Yeah, I think this enumeration is pretty good actually. Yeah, I think this enumeration is pretty good because I think it just naturally gives a way to uh, cope with this restriction, right? Because here, because we start with 1 and then we go outside, right? So it's like when this n is getting larger and larger. So for example, you're expecting like the points to sort of winding around the origin, like in terms of bigger and bigger radius, right? So here, for n being large, right? So this radius 2r. So for example, we have because we are interested in like the omega for omega bigger than 2r, right? Because for omega bigger than 2r, we can use this one as a bounds. So there exists n, right? So basically there must be a point where sort of, right? So basically if you add like the nth barrier, right? So this is the first loop, second loop, like the nth loop. For example, or some n less bigger than this 2r, right? This is 2r. And then if there is some n that's bigger than this 2r, so maybe I draw it here. And then when you are at this loop, right? And then everything is outside this 2r. So actually, I think this enumeration is pretty suitable for this scenario. So, yeah. So, yeah. So here, I think we also need to define this because here it says so the average M test is an argument about the sequence, right? So it's an argument about the sequence of functions. So I think here we need some argument about, because here what we want is that we want to determine whether this series is converging or not, right? So here, in order to use the wire stress M test, so we have to define each finite sums. We define the partial sums, right? The sequence of partial sums, right? And we want to show this. We want to show this condition for the sequence of partial sums Fn in order to show the convergence. So therefore, what we do is that we let capital F of n, so it's like the n sum. So maybe I'll use just Sn to use the nth partial sum. So maybe I'll use letter I. So be the partial sums 1 over z minus omega. Sorry, it should be omega I, and then plus 1 over omega I plus z over omega I squared. So this is the partial sums. So it should be in terms of z, right? So because we are, so this is the functions, right? So this is a sequence of functions. So these are functions. So and then what we have is that so now, okay, so we want to show that this is bounded. So why this is bounded? Yeah, because of this argument, right? So by the construction of the left, by the construction of the enumerator, yeah. So by the construction of this omega n, so we know that there exists an n such that we know that, right? So we know that there is an n that when this n is large, every lattice point is at outside the radius, right? So I mean like in this case, I think this omega 1 omega could or omega 2, they are like standard, right? So they are just parallel, like perpendicular. But in general, right? So in general, we can find like we can take n to be like because in general we may have like this guy, so we can take like the loop to be because here, for example, in this one is like longer, so maybe just take 2 steps, right? 2 barrier you would get outside this radius 2r, right? So when this one gets into the radius 2r, then like when you go around here, so every point is going like away from the radius 2r. So however, we also need like this direction to also get away with the radius 2r, right? So maybe here it may take 3 steps. So maybe we choose n to be the maximum among those the maximum between these two, right? So when we take the maximum, so this part is outside this radius 2r. The shorter one is outside it's getting outside of the radius 2r, and then the longer one is also getting outside the radius 2r, maybe even like longer. And then at this stage, like every point, it will be outside this disk of radius 2r. So we know that by construction, we know that there is a n bigger than 0 such that so the modulus of omega n is bigger than 2r for n bigger than this n. So so therefore yeah, so therefore I think what we can do is that, because we need to show that this first, so I think there are 2 arguments, right? So one thing is that we need to find like a uniform balance, like we need to find like a total balance for this sequence of partial sums, right? I think in this case there is no problem because yeah, so why there is no problem? Because yeah, because so when so first, right, so when this n is large, right? So I think basically we break this into 2 parts, right? So one part is the part where this n is small. This n is less than this capital, less than or equal to this capital N, right? So in that case, the thing is that for each of the n, that's n where n is small, so we can just take the because it is there are finitely many terms, right? So finitely many terms, we don't need to worry about because we have to have we have to have the bounds. So for each n, right? For each n, we need to find a bounds that bounds the partial sums, that bounds the partial sums. So, and then we also need the bounds to be summable, right? So namely the sum, the sum, they are summable, right? The sum converge. So, but when for the n that's being for those n's where this n is less than equal to the capital N, so because there are finitely many terms, right? And for each of the term, the bound is just a finite number. So why is a finite number? Because for each of the SNs, right? So these SNs they are so these SN they are a so why we have a bounce for these SNs? Because these SN they are oh, actually, I think I'm wrong. So why I'm wrong? Because yes. So oh, actually, I'm not wrong. So yes, because here yeah. So what we want to do is that in order to show the convergence, we want to construct a compact subset, right? Because we want to show that this sequence is converge uniformly. Yeah, we want to show that this sequence have uniform absolute convergence on compact subset over one in the lattice. So yeah, so I think maybe there is some problems when the z is equal to is near the value of the lattice, right? So it may blow up for this function. But the idea is that when we take compact subset, right, the function is bounded on the compact subset. So it just naturally gives us the upper bound for the modulus for the absolute value of the function. Yeah. So for the finitely many terms that's less than n, so we just take these mn to be their upper bound given by the compact subset property. And then because they are finite, so they just sum up to a finite number. And then for the rest of the part that's bigger than n, so what we do is that we will use this guy. So we showed in this property that when the z is less than radius r and then omega n is bigger than 2r, then the whole thing is less than equal to this guy. And then so we let this guy to be our mn for n bigger than this n. And then because this guy is summable, right? So we know that this guy is summable. Basically, sum is finite. So therefore, when we add these two terms up, it is summable. So we combine these and the finite sums. So it is also finite because this is finite and the finite term is also finite. Yeah. So I think that's our argument here. So so we know that there is n such that omega n is bigger than 2r for n bigger than n. So yeah. So I'll write it down. What I said. So we know that there is an n such that omega n bigger than 2r for n bigger than n, and also so also we know that also sorry. Oh yeah. So So what do you what do you want to show? So okay, so let's start with the finite. So that's first. So okay, so here, so then um, um, okay, so we fix a compact set, right? So because we want to show that, so this is so we want to show that it is we want to show that it has a uniform absolute convergence on compact subsets of one lattice. So basically, because this wire stretch M test it requires a set A, right? So it is yeah. So we just then that so K be a compact subset of C take away the lattice which is being defined there, and then so be a compact set and then so what we're gonna do, so we're gonna construct this element, right? So so first maybe we can construct the upper bound for this n being small, right? So then so again, like these fn's they should correspond to the partial sums, but for the upper bound, right? So remember, for the upper bound, we can only construct the upper bound for each of the summand terms, right? So so that the upper bound for this Sn is just the sum of the upper bound of the summand. Yeah. So we want to construct the upper bound for the summand terms. So then for n less than equal to n. So for any n less than equal to n, we let this mn to be equal to the supremum of the z in k of the summand function of the modulus of the summand function, right? So z minus omega n plus 1 over omega n, and then plus z over omega n squared, right? Sorry, it's so yeah, so let me just erase this part. Yeah, I want to keep this one in order to so and then so yeah, so here we have already defined the, oh sorry, so this is not mn, so this is just the, so mn should be the bound for this partial sum, right? So this is just the upper bound for each summand. So maybe I'll use an to distinguish this mn. So and then what I have is that Yeah, so here, right, so this is the upper bound for the summand when this n is less than equal to this n. And then we also need to define the upper bound for the summand where the index is bigger than n, right? So, and also for so now for this, so for any n bigger than n, so we let a n to be maybe I'll use bn to distinguish these two different types. So now the bn's, right? So now we know that we can let bn because here this omega n is bigger than 2r for this n bigger than n, so we can just let bn to be this guy, 2r squared. Yeah, because now this K is a compact subset. Okay, so maybe okay. Okay, so maybe I think there is something wrong. So we are compact set. So maybe we want to pick this R to contain this K, right? So otherwise we won't have this condition because this argument only applies when this modulus Z less than or equal to this R, right? Yeah. So we choose this n based on the radius, right? So here, so we pick the radius to be that contain this K, right? So and then we pick, so because the argument before is just any R, right? So now we pick the R to be pick the R such that it contains K, right? Such that maybe the disk contains K. Okay. Okay. So now so now we let Bn to be so now this is true, right? So this is true. And then we pick this n such that this omega n is bigger than 2r, right? So this R. So now this Bn is equal to 2r squared over omega n cubed. So and then therefore we have that let's see. So then this property holds, right? So now so now maybe that's so maybe let me just do this. So now this Sn, right, is the modulus of Sn is less than or equal to the sum, right, of the modulus of this guy and then we break it into two parts, right? So the parts where this n is less than or equal to this n, and then of the sum plus the sum where this n is bigger than n, right? So this part could be equal to 0. So and then I just denote this one as our, and then we define this one as our Mn, right? So just yeah, just call this Mn. Okay. So namely like yeah. So and then we need to try this sum of this Mn converges. Wait, hold on 1 second. Oh shoot. Right, so this argument is about infinite sums, my bad. Yeah, so this argument is about infinite sums. So therefore, this should be my Mn, right? And then this should also be my Mn for n large, right? And then I don't need to care about the partial sums, right? I just need to care about the sum of Mn's, okay? So therefore, I don't need to care about the partial sums anymore. So now, okay, so everything is the same. And then besides, I'll just let f and z to be just this guy, okay? Sorry. Yeah. So here, right? So for this f and z, right? So when this f and z is small, then it's bounded by, we use this bound for when f and z is small, and then when f and z is large, then we use this bound for the f and z. So therefore, the sum, and then we need to show that the sums of the element convergent, right? Yeah. So this is equal to so here I'm doing in an informal way, right? So basically, so yeah, maybe maybe I should write this, right? So first, so for the finite sum, right? And then plus the infinite sums. So this because this is a finite number, right? So I call it C, right? I just call this a finite number, and then this is the sum, right, of this guy. Yeah. So we know that this is called convergence. So therefore, it's finite. Yeah, because you just hi.
12? No?
Huh?
It's not 12?
Oh no. Yeah, thank you. Yeah. So so in this case we show that so this is a finite sum, right? So and also so we know that this Fn is it's of course less than or equal to Mn for the large. Yeah. So yo, what's up?
你看他干嘛？你看，怎么录像干嘛？
讲课。
讲干嘛呢？
啊？
你结束了吗？还是没有？
还没有。
嗯。 数学啊，这种东西，对，没有一些 complex analysis。剪给谁的 ？YouTube 关注。
So yeah, so this is my friend. So Richard. 哎，介绍一下。Hi everyone, this is my friend Richard. So he is also a PhD
Hello, everyone.
behind statistics at Harvard. Maybe he can join me if you want.
Joining you, right?
Yeah.
What's the course name? What's the topic here?
So we want to use the Weierstrass M test to show the convergence of this function. So we have
Complex analysis, right?
Yeah. So we have a sequence of functions like that.
Yeah.
So this omega n it is being defined as omega n basically is being defined as the points that's so here this do you know analysis? So basically you have a two complex you have two numbers, right?
Mm-hmm.
So omega 1, omega 2. And then you define like all the linear combination of these two. Like omega 1 is a vector like that, omega 2 is a vector like that. And then you add the two up.
Okay.
Yeah, and then you derive like that is. So yeah, basically we want to show this is convergent.
Oh, that's a
Yeah. Yeah. Do. So yeah, I think the difference between like the one branch of math and the other branch of math is very huge. So it's very hard for yeah, because I think that's the different people in different. Yeah, it's just like the barrier is very large. I think for different fields of. Yeah, it's just like in general, you may imagine that in reality, like we have different jobs, right? So there might be a huge gap between like a software engineer and also like a engine development or engine repair. So yeah, so just or like some I think that's basically the same in like in like a math. So different people in different field, their specialty is very different. So it takes it's reasonable. It's just like a normal situation for like other people, even though he's also a PhD, but he may not understand so well about a criterion that's not in his field. Even though he may understand his field very, very well. So it's just like the gap is very huge. Yeah. So so let's go back to this case where yeah, so we show that this M is converging, right? So we just show this one, and also yeah. So since So here, this all these two conditions of the Weierstrass M test are satisfied. So the Weierstrass convergence M test. So implies that the sum infinity of these fn's so converge absolutely and uniformly on this K, right? And then yes, so and then since this K is arbitrary, so this statement I think this statement is true, right? So so we just finished the proof of this statement here. So in this case, this zeta z is well defined, right? Because we have the absolute convergence. So absolute convergence just implies that the sequence is the limit stays the same under any rearrangement. The limit exists and also stays the same under any rearrangement. So so now we are done with the first one. And then, so what about the second one? So do I have time for the second one? Okay, so maybe I think it's a good place to end. Okay, thanks.